Welcome back. We will go to the two-port network analysis. This is the two-port. We have seen in Z and Y parameters also. There are two. Each ports will have two wires, one pair, and we have an input port 1, and here the output port is 2, and the incident wave is given at port 1. This two-port networks can be anything, can be isolator, can be alternators, can be filters, it can be modulus or RC filters also. So it can be any device. It's like a black box. So I've given an input wave at port 1. So like truly speaking, if at low frequency I will expect after filter, when I use the filter output, I obviously get the filtered output. That's what I give input, I'll get output. I won't look other kind of aspect of it. But when I come to the high frequency, I have to look back. I have to look at, if I giving an incident wave, what is the output I'm getting? That is a transmitted wave at the second port. And meantime, what is the wave? How much part of the wave is coming back to the input? That is called reflector. Okay, this is what important phenomena in the high frequency microwave circuits and transmission. So when I give an input, the transmitted wave, I am getting output, and meantime how much signal of transmitted wave coming back to the input, that is called reflected wave. This is coming, as mentioned previously, it is coming because of if this two-port network, if it is connected in op-amp or any other antennas, if that port is not masked correctly, there is a chance it can come as a reflection to the two-port device. So I'll start getting a reflected. Not only that succeeded devices, it can be in the two-port device design itself if the input port is not masked correctly. So there I can also possibly get the reflection. Okay, this is a scenario, we will get it in the two-port network, high frequency two-port network devices. So that is what here, some of the here is reflected back. So let us take the two-port networks, all the incident and reflected voltages. This is the normal notations we will define in two-port. This V1 plus is incident wave at port 1, V1 minus is a reflected, that is a green color. And if the wave is transmitted after second port, it become a V2 plus minus, because it's a reflected. You should be careful about sign here. Whenever incident voltage V1 plus is incident on second port, it is coming to is transferred to the output from the V2 minus. Means that if you take at the second port, if you look at the second port, the reflection at second port is nothing but coming away from the second port. It's nothing but V2 minus, that is coming from, reflected from second port, that is V2 minus. In the context of the input, this is called transmitted wave. Okay, if you look from the first port, when I give the input V1 plus, this is what coming out as the output, that is called transmitted wave. If I look from the input port 1, if I look into the second port, it is reflected from the second port. That's why it is a negative sign, V2 minus. And V2 plus is the voltage which is incident to the second port, that can be coming from the other system connected to this cascaded system. Any device is connected to this, due to that there may be a reflection coming from there, that is V2 plus. And this V1 minus is the reflected from the first port. It can be reflected from the first port, or part of the V2 plus can go into V2 minus. I think, is it clear? So here, so part of the V2 minus can go to V1 minus. So part of V1 minus, part of V1 plus, it can go into V2 minus, transmitted to here. This V2 plus can go to V1 minus also. Okay, so these are the four voltages in the two-port network. Yeah, in the two-port network, we have a 4 voltages. That is a incident voltage V1 plus at port 1, and reflected is V1 minus at port 1, and V2 minus is reflected from the second port, and V2 plus is incident to the port 2. So this is a common notation. This can be also written in different notations, but I am following in the textbook, so it will be a standard way of representing it. So if you write the S matrix as we have seen earlier, so the reflected voltage at the left side V1 minus and V2 minus equals to the S matrix of two port S11, S12 and S21 and S22 of incident voltage V1 plus and V2 plus. So here S matrix as we mentioned displays a blueprint of the device, how the device is working from, we can find out from the S matrix. So I just want to tell you in the practical perspective, if we buy any devices, so in the data sheet normally they give S matrix values. So from that I can find out what is for example the voltage or power from the different port on the device. I think it should be clear. And as I told, V1 minus and V2 minus is a reflected voltage that can be also written as a B. For example, this is V2 minus, or reflected I can write as a B2. This is a B2. Okay, and this is my other reflected, I can write B1. Okay, so this is I can write B1 and B2, all the either V1 minus or V2 minus I can write, or B1 B2. So reflected voltage can be also written as a B coefficients, and incident also can be written as A coefficients. This is a different way of telling it, but it's better to follow one way of representing it. So keep it in mind, and some way, somewhere we'll use that as a coefficients. So here V2 minus also can be written as B2. This is B1, reflected voltage, B coefficients, incident is the A coefficient. This can be written as the A2, this can be A1. So S matrix, as we mentioned, just saw that can be written like this. So this can be also written as B1, B2, S11, S12, S21, S22, A1, A2. So this is another way of representing it of S matrix. In the S matrix I can write it in the reflected incident voltage either way. So then we will go into little further to two-port network. So what these S matrix refer to? So I have for example, so I have a different S matrix, S11, S12, S21 and S22. So what actually it mean for in the two-port device? So what is S11 mean for? If I send an incident voltage V1 or A1, so if it is reflected in the first port, if I take a ratio of these two, it becomes S11. So S11 refers to the signal reflected at port 1 for the signal incident at the same port 1. So the scattering matrix is V1 minus by V1 plus. This is, I told, this will be closely related with the reflection coefficient. At port 1. Okay, I think I can rewrite this. The reflection coefficient at port 1 is nothing but S11, provided that V2 plus equals to 0. Anyway, in the general, I can write S11 is equals to reflection coefficient at port 1. And if you see what is S21 or S12, here is S12 is nothing but the first number will tell me always the output and second number will tell me where is the input. So here what is the output at first port, that is reflected at first port. So reflected is negative and first port is V1. So what is V1 minus reflected divided by what is the incident? It's the incident voltage from the second port. So V1 minus divided by V2 plus. So that is my this is my S matrix for S12. So where this scenario we will use it in the practical. Some cases if we want to see that what is a successive device is the reflected voltage to measure it, so I can use that S12. So what is S21? It's a inverse of S12. What is output voltage at second? That is V2 minus, reflected from the second port, V2 minus. And what is the incident? It is the V1 plus. So what is S21 parameter? Is nothing but V2 minus divided by V1 plus. What is S22? It's similar like S11. What is reflected at the second port and incident also the second port. So S22 is nothing but V2 minus divided by V2 plus. Or the different notations I can write, it can be written as B2 divided by A2. This is also to find out, this is also closely related to what is the reflection at second port. It's nothing but S22, provided that V1 plus equals to 0. So nothing, we have to keep it in mind. Okay, if there is no reflection, if any port, if it is perfectly matched, this second port is perfectly matched, so what is the value of S22? This is again another important inference you can get. So here, if this port is perfectly matched, means that there is no reflection from here, this port to here, there is no reflection. So V2 plus the incident. So what is the reflection from this port? Sorry, here there is no reflection here. V2 minus, okay, is supposed to be a 0. And what is the V2 plus is supposed to be any quantity. What is the S21 value? What is the output at 2 from 1? Okay, so there is a, sorry, this is a supposed to be S22, right? There is small changes here. This is nothing but S22, okay, not S21. So it's nothing but V2 minus divided by V2 plus. So what is the output voltage? That is, what is the reflected voltage here? I'm incident some voltage. So instead of sending input here, I'm using this as the input. Maybe I'm sending 1 milliwatts power here. If there is no reflection, there is V2 minus equals to 0, and V2 plus is 1 milliwatts square root, because it is in the voltage, this is the power. So some voltage, arbitrary voltage, V2 plus is there. So if perfectly matched, if the output port is perfectly matched, S22 becomes 0. So what is the gamma 2? Also 0. Reflection coefficients also will be a 0. If the reflection coefficient is 0, I can see that there is no reflection, so the port is perfectly matched. Similarly, S11, what we have seen that if S11 equal to 0, so that ports are perfectly matched. So the S matrix of a matched port of either matched at first or matched at 2, if the two port network is matched in input and output, can be written as S11 is 0, S22 is 0 and S12 S2. And also if the devices are symmetric, if I able to interchange the ports, so S12 should be equals to S21. That is Sij if equal to Sji means that both are interchangeable. Instead of giving input here, I can give the input here also, so I can use that. Okay, if the ports are interchangeable. So if ports are matched, all the diagonals is 0. If the ports are symmetric or reciprocal, Sij equal to Sji, that is, it's a symmetric matrix, that is a transpose of the matrix equals to the original matrix. So that case I can write S matrix as 0, S12, S12 again, because S21 equal to S12 again 0. So this is a lossless, this is a symmetric and also matched two port network. Whether if it is lossy or lossless, again we can find out with some property that we will see it shortly. So this is what the properties we call, this is a 3 properties, important properties of S parameter. In Z and Y we have seen that the symmetric property, just now we have seen that, and also matched, not matched, it is a lossless property. Okay, here apart from 2 we have one more property called matched. If it is matched, all diagonals of S matrix will be 0, S11, S22, S33 and so on will be a 0, and that is a matched property. And other than that, there is a property symmetric, reciprocal. If transpose of the matrix, if it is same, that is a symmetry port, so I can use the device interchangeably. And other property is lossless or lossy. And is a Y parameter, if it is a lossless, all the Z or Y parameter values will be only the imaginary numbers. If any part of element, if it is a complex real plus imaginary number, then it is not a lossless, it is a lossy device. In the S parameter, we will also find out whether device is lossy or lossless with using another property. Now we will see the matched property. If it is matched, all the ports are matched to the characteristics impedance, then reflection at every port is 0, that is a matching property. From the equation Sij equals to, this is general for any ports, this is Vi minus first number is output, Vi minus reflected and Vj plus the incident. So if it is SII, because if it is a matched with the same port, if I take the output and the input also same port, reflected voltage at port I and incident voltage at port I, both are same port. So that time reflected voltage, if it is ideally, if it is 0, then reflected voltage I will get 0. If it is not, it will have some other value. Okay. So here if incident voltage is not a 0 and reflected if it is 0, so S11 becomes a 0. So if it is perfectly matched circuit, so S11 or S22 or gamma 1 or gamma 2 is equals to 0. That is a perfectly matched circuit. From the S parameter, S matrix, I can find out if diagonals are 0, then that device is matched, all the ports are matched. In case if you take a 2-3 port network, if S11 is 0, S22 is 0, but S33 is not 0 means, if it is not 0, but rest of the element, some values will be there. If a diagonal, if you not all elements are 0, then we cannot say all the ports are matched, but these two ports are matched. That is S11, S22 equal to 0. These ports are matched, but not S33. This port is not matched. Second property is symmetric, that is a reciprocal property. So reciprocal property we have seen in the Z parameter also. If it is S and transpose of S, if both are same, then we can say that is a network is reciprocal. That is easier way of finding out from the S matrix is, let us take a 3-port network S11, S12, S13. Let us take S12 equal to S21. So S21 also S12, this is S22, S23. So let us take S13 equals to S31 because symmetric port. So S13 equal to S31, and let us take S23 equals to S32 or S32 equal to S23. So these also become, sorry, this has to be S13, this has to be S23. So this is S33. So if the network is symmetric or reciprocal, so it will be a just Sij which is equals to Sj because both are symmetric. How you can see it in the S matrix? If you look at S matrix, take a diagonal as a reference. Maybe I'll choose another color. So if you take a diagonal, so with respect to the diagonal, if you take the top elements S12, S13 and S23, this is, if you look at the bottom elements, this is just a mirror. Okay, if you just keep on mirror, so this top portion is nothing but a reflection of bottom or vice versa. The bottom portion is nothing but reflection of top portion. So it's nothing but transpose of the matrix. If the matrix and transpose of the matrix, if it is same, so we call that is a symmetrical network. Okay, third one is one of important properties, lossless. So from this matrix, how I can say that if device is lossy or lossless? What we have to do is either we have to find out whether it is satisfying the unitary property. So as I mentioned earlier, if you look at the lossless network, there is no real power delivered to the network. The network that doesn't consume any power, only it will pass the power. So it cannot consume or alternate power. So this is called a lossless. So to any networks to be lossless, there should be two conditions should be satisfied. One is the unitary, one is a unitary property, another is a zero property that we will see shortly. This is a unitary property. You take one S matrix, from the S matrix take one element, take a conjugate of the same element. So if you take S and conjugate of this, if you take one complex number, conjugate of the complex number, what you will get? You will get a magnitude square. For example, if you take a plus ib, I think all of you know this. What is the conjugate of a plus ib? It's a minus ib. If you multiply that, you get a square plus b square. Okay, or if you take a kind of magnitude, this is a square plus b square, or if you take just a what you say, the magnitude of a plus ib, so root of a square plus b square. Okay, take a square of this. It's nothing but a square plus b square. This is nothing but taking a complex number and conjugate of it. It's nothing but taking a complex number magnitude and square it. Okay, when you multiply complex number with a conjugate, you will get a magnitude of the complex number to the square. Okay, so if we take a two-port network, this is S11, S12 is, sorry, so if it is only two port, this is S21, S22. So take any element, take elements from the first row. S11, take a magnitude, square it. Take a second element, take a magnitude and square it. If it is equals to 1, then we tell us this is a lossless network. It is very important and useful. Just look at this matrix, take a magnitude square on the row, add everything. If it is coming 1, it is a lossless. If it is not equals to 1, it is a lossy device. Okay. Similarly, you can take a second row and you can do it. So other property, the same lossless network is a zero property. Now this time you take one element from the first column, take the second element conjugate of the second column, multiply it and add everything. So you will get, supposed to get 0. Okay. So for a practical problems, for example, if you take a like in a two-port network, if you take a first column S11 and second column conjugate of it, multiply it, so it has to come 0, or second row first column and second row second column conjugate, if you multiply it, it's supposed to come 0. So in general, we can either find out whether it's a lossy or lossless by using a zero property or unitary property. So it is easier to find out by using a unitary property. So in problems we will normally use like a unitary property to find out whether device is lossy or lossless. So this is one of the important aspect of this parameters. If any problems given to solve, to find out whether which are the properties are satisfied, which are not satisfied, so we can use that these concepts. So next let us go to one problem quickly. So in a two-port two-port network is known to have following scattering matrix, that is 0.25. As I told you, S matrix can be a complex number either in a rectangular or polar format. I think if it is a magnitude and angle is there, it is a complex number in the polar format. So it's a given two-port network, 0.25 and 0 degree, and 0.9 minus 50 degree, and 0.9 and 50 degree, and 0.150 degree. So find the two-port network, whether it is matched and reciprocal or lossless, whether the three properties, which are the things are satisfied, which are is not satisfied. So you take a first row and take a magnitude of first element square, and first row the magnitude of second element square, and when you find out if this is not equals to 1, so this is not a lossless device, it's a lossy. So there will be some alternation inside the device. So next we'll go to the reciprocal or symmetrical property. So if you take the diagonal elements, we don't need to worry about the diagonal. Apart from diagonal, if you look into it, these are diagonal elements. Okay. So apart from the diagonal elements, if you look it into S12 or S21, if S12 equal to S21, then we call as a symmetrical or reciprocal. Since this is real, magnitude part is same, but the angle is not same, so this is not symmetrical, so it is not symmetrical device, it's not a reciprocal. Okay, I cannot use this interchangeably the ports. The third property is whether this two-port device is matched. For a matching property, I have to go to the diagonal and see that if diagonals are 0. If diagonal, if it is here it's not 0, so this is ports are not matched, and first port and second port there will be a reflection. If I apply the input voltage, there will be some reflection due to the mismatch, so the ports are not matched. So this is a solution for given problem. You can solve many this variety, different variety of these problems, and to get a better understanding of S parameters. So I'll stop here. I think it's quite a little long videos, and we will continue in the next lecture. Thank you.